On the screen behind me here it says a reintroduction to acid-base chemistry, because you did a lot of acid-base chemistry in grade 11, but we're going to change it up. If you think back, we had something called the Arrhenius definition, and we did strong acids, strong bases. So let's recap that. If you like to write things down, you don't really need to write down the Arrhenius stuff. This was our grade 11 definition, and we're going to change it. But just to kind of refamiliarize yourself with a couple of ideas. One, what do acids look like and what do bases look like? Why do we talk about strong acids or weak acids? And what's the acid part of an acid? So that's kind of on this screen here. So take a moment to read it, but there's no real need to write it down because we're going to bust it all apart. Let's take a closer look at that hydrogen, because we talked about the H plus and where does that come from, what does that mean? If I take a hydrogen atom, one electron, one proton, if I make that a positive ion, what do? Well, I lose the electron, and at that point all I'm left with is a proton. So you're going to find that we talk about acids that and they're protic or monoprotic or diprotic or something like that. That protic part is going to come back to it. It's also going to come back to it in the definition that we use, which is based on the Bronsted-Lowry model of acids and bases. And yeah, Bronsted had a weird O in his, or weird letter. It was, I think he's Danish or something like that. We're not going to be doing the spelling test for it though. Okay, under their definition, an acid is now considered to be a proton donor. And if I take a look at the acid that we had on a previous one, a very common acid, if I look at that as it, well, last year we would have said dissociates and then reacts with water. If it just treated as a react with water, if I look at where the hydrogen chloride, the HCl, started and how it finished up, I notice that it's lost a proton. And so the water has then in turn gained that proton. The proton went to the water, making the hydronium ion, the H3O plus. And if I look at a different acid, and you'll notice I've got the equilibrium arrows, and we'll talk about that later. So I have this acid, and I donate the proton from the acid to the water, and I end up with, you're right, Bro, which somebody wearing a periodic table shirt probably shouldn't be saying. But I donate the proton from the acid to the water. Bases, on the other hand, instead of being something that increases the concentration of hydroxide, a base then is something that accepts a proton. Now we do need to be careful when we talk about donor and acceptor and things like that. I don't want to make it sound passive or active or anything else like that. It's just, where does the H plus go and where does it come from? So base then is a proton acceptor. So if I take a look at a weak base here like ammonia, NH3, and when it goes into water, it does generate some hydroxide. It is a weak base. But how does it happen? Well, water loses a proton, a hydrogen with a plus charge. So I go from NH3 neutral to NH4 plus 1 charge. I've increased it by hydrogen and a positive charge. And if I follow that through, then the proton has come from the water. But if I look at how one changes to the other, I've identified that the base, the NH3, has accepted the proton. Other bases, or other things that can behave as bases, will do that as well. Now you'll notice I haven't got the traditional hydroxide base up here, and that's going to come back in a little bit, probably not today, but in a few days from now. So certain acid-base reactions are then reversible, which makes sense. That's why we're dealing with it in our equilibrium topic. If I take a look at this one, I identified earlier the acid and the base, and water in this case is behaving as the base because it is accepting the proton. But if I were to look at the other side, and I were to follow it from the products back to the reactants, then the Bro is now going to become the proton acceptor, and the H3O plus is the proton donor. So if I look at that as going a forward direction, as written, or reverse direction, as written, then what I end up with are kind of opposites on either side. So the water starts out accepting the base, but once it's accepting the proton, but once it's accepted the proton, it can turn around and donate the proton. And same thing with the HBRO, that would be hypobromic acid, or hypobromous acid rather. And then, as I mentioned, the water. And other weak acid reactions or weak base reactions will do the same kind of thing. If I look at this one, this was the example I used for my weak base. The thing that starts out as a base, accepting a proton, becomes something that can donate a proton. And if I were to follow both from either side, both are different by 1 proton. That leads us to something called conjugate pairs. And a conjugate pair are, on these specific examples, the hypobromous acid with the hypobromite ion is an acid and its conjugate base. So that's an acid-base conjugate pair. And then the other one, with the water and the H3O+, that's a base and an acid conjugate pair. And if we did something kind of similar, then we would have, in each one of those things, we would have a couple of acid-base conjugate pairs. It doesn't really matter which one is which in terms of they can still be a conjugate pair, but a conjugate pair is always different by 1 proton, and that's it. The base accepts a proton, which then gives it a proton it could donate as an acid. All right, why are we using water a lot? You might be wondering, what's going on with water? It was behaving as a base, it was behaving as an acid. We have the term called amphoteric, and that means it can either donate or accept a proton. It kind of depends on what it's reacting with. Is it reacting with something that's a better proton donor? The base, then the acid, try that again, the water will be forced to then accept it. I think I left off with donating. If it's reacting with a stronger acid, a better proton donor, the water is forced to be the base. If water is in the mix with a stronger proton acceptor, then water is forced to be the acid and donate its proton. Water can also do something called autoionization, and that's where a water molecule collides with another water molecule to make hydronium, H3O+, and hydroxide ions. And there's an equilibrium there, obviously, so I could look at the concentration of the reactants and products, and of course, solution versus liquid, so it looks a little bit different from what we might expect. It's got a very, very small equilibrium constant. And in a neutral solution, where the only thing that's happening is the autoionization, no additional hydronium, no additional hydroxide, I would end up with concentrations of 1 times 10 to the exponent -7 moles per liter, which is really, really, really tiny. Tiny to the point that we normally ignore that. But, by the way, by way of comparison, water itself is about 55 and a half or 55.6 moles per liter. So that 1 times 10 exponent -7, we can easily ignore that. But it's got some other interesting things going on that we'll talk about another time. Sometimes in this I was using straight arrows, sometimes in this I was using equilibrium arrows. When do I use which? Easiest answer is, for most of our work, it's going to be the equilibrium arrows, because we're talking about equilibrium, right? But strong acids from grade 11, 100% dissociation. And if you were thinking about what that means if I take an acid molecule and represent it like this, and I take a bunch of those, and if I were to put those into water, then not only would one of them dissociate into its ions, all of them would dissociate into its ions. And at that point, then a straight arrow makes sense, a non-reversible reaction, because 100% dissociation means that there are none of the products going back to form reactants. And there were 6 strong acids, and again, we learned these in grade 11. We don't really need them so much now, but it's not a bad idea to always remember your 6 strong acids. We're going to be more interested in weak acids, and where weak acids have less than 100% dissociation. Now, I know technically that could mean 98, but in weak acids it's usually much less than 100%, closer to 5% or less than that. If I were to take the same 5 acid molecules, not the same 5, but now weak acid molecules, but 5 of a weak acid, and I put those into water, yeah, some of them would dissociate because that's what acids do, but most of them would not. At which point, I'm talking about an equilibrium. Because let's say one of those new ones break apart and a couple of those ions then recollide and form back the acid. So then I have that acid-base equilibrium set up where I've got the conjugate pairs and where everything is in the mix, and I have to pay attention to it all. You might be wondering about a list of weak acids. It's a really, really long list. So what we'll do is we'll remember our 6 strong acids, and then anything that's not a strong acid is automatically a weak acid. Sometimes, for the sake of keeping things nice and neat, we'll abbreviate our weak acid as HA. H, obviously, for the proton, A for the anion. I know you thought I was going to say the acid. The anion of the acid. Okay, bases. We want to cover all of our topics. Strong bases, similar to strong acids, 100% dissociation. We had a fairly weird looking list last time because it really consisted of sodium hydroxide, potassium hydroxide, but really it would have been all of the group 1 hydroxides and then some of the group 2 hydroxides. The problem with group 2 hydroxides is that a lot of them aren't very soluble. So you can, on paper, say that it works, but you can't really make much of a solution out of a group 2 hydroxide or most other hydroxides. We're going to be more interested in weak bases, which, like weak acids, show less than 100% dissociation. And they often don't immediately have the hydroxide in them. If you think back to the example I used earlier, and then other compounds where nitrogen is an atom involved, they can also do that. At this point, all we've done really is identify acids and bases, talk about the different definitions, and you should then be able to, using that definition, identify what the conjugate pairs are. Remember, it's a difference of 1 proton. So H2O to OH, or H2O to H3O plus, and I missed the minus on my OH a minute ago. And also, given a weak acid or a weak base, write the equilibrium expression for it, where it's donated a proton in the case of an acid, or accepted a proton in the case of a base. After that, we're going to set up some ice tables, and we're going to do the calculations, and that will be, you get lots of practice at that.